The water energy nexus, or the interrelationship between water and energy, is becoming an increasingly important topic. First, there is water for energy. It takes a substantial amount of water to generate, transport, store, and use energy. Then, there's energy for water. It takes a significant amount of energy to collect, clean, move, store, use, and dispose of water. However, most research done on this relationship is at a coarse resolution. For example, how much water is being consumed in thermoelectric power plants in California, or how much energy do wastewater treatment plants use each month. Our research evaluates the water energy nexus at a fine resolution and at the end use, using customer-level water and electricity consumption data. Using statistical methods and machine learning techniques, we are uncovering new relationships between the two natural resources across different timescales and within residential, commercial, and industrial sectors. One topic that we are investigating is how conservation and efficiency measures aimed at one commodity impact use in the other. For example, given the current drought across the western United States, many water utilities are incentivizing residential and commercial customers to remove their traditional turf lawns through cash for grass programs. However, wide-scale vegetation removal can also create an urban heat island effect, increasing peak energy demand as customers use more air conditioning. Through our research, we hope to increase knowledge of urban water and energy use patterns while providing useful information to decision makers that can help them better understand demand, policy implications, and management techniques.
We're going to talk about water this morning as a critical resource, and it's of course critical to all of us in many different ways. We'll talk about sort of unconventional resources, which has been a theme of the conference, and we'll talk about water in sort of the conventional oil and gas industry. And I'm going to get started by asking a specific question to each of the panelists, and then we'll open it up to your questions as well. And my first question is for Steve Mueller. Southwestern Energy has been a real leader, and you made a commitment to become freshwater neutral by the end of 2016. Now we're just about in February of 2016. So can you tell us about your decision to make that commitment to become freshwater neutral and the progress you're making toward achieving that goal?
Sure. You know, we actually started this in late 2012, and we were looking at our company, we were looking at the industry, and there's a couple things that we noticed. We noticed first that, and I talked a little bit about yesterday on the innovation panel, just moving water, if you do it very ineffectively, it could be as much as 30% of the cost of your well. If you can get that down to an efficient level, it can be less than 10% of your cost of well, so there's some cost savings that can be involved. The other thing we noticed is that you've got all the things about what happens to the water and frac fluids, and I'll talk a little bit about that. But when you frac a well and you do the stimulation, about 70% of the water gets left down in that formation. So you're actually using water, not just doing something else to the water. And then the other thing that was very evident to us is wherever you worked in the country, there was a lot of different things that went on. And to put this in perspective, we're the third largest gas producer in the United States, and we do work in all the major unconventional regions. So we had to put all that together. And so in 2012, we thought 2016 ought to be an easy goal. We should be able to go out and do this. It took us over a year just to figure out how to standardize the measurement of water across our company. And as we standardized the measurement of water across the company, we came out with basically 4 different principles that we set about trying to become freshwater neutral. And the first one was one we carried over from what we were doing, and that was just protect. Protect the water from getting in the wrong spots, protect the water from leaking, protect the water at the surface, protect the water downhole. And there's a whole lot of things that go with that. Part of that has to do with how you drill the wells and wellbore integrity. Part of that has to do with educating your employees, and they talked a little bit about it yesterday, the vendors, being wise about water. And part of it had to do, frankly, with the completion and how you do the completion and making sure that whatever you put down hole has the least environmental impact in case something does happen. And we put programs in effect. Then, as I said, since you're leaving a lot of the, as you're thinking about it, the next big principle we had was we needed to reduce what we were doing. And we can reduce what we're doing in freshwater two ways. The first way is just physically reduce it. And we went about looking at the major source that we use for water, which is in the stimulation work that we do in completion of the wells. In the one area we worked longest on so far, we've reduced the water use per foot of well we complete by 30%. And we've done that with increasing the productivity from the well and increasing the other characteristics that you do in the stimulation. And that was all a bunch of science, so we went on that one. The other thing about you do about reducing water is using alternate water. So you reduce the fresh water by using some other source, either brackish water, reusing the water you've taken from the surface in completion, or in whatever you've got from produced water. Today, we're reusing about 99% of the water. And we put in effect in early 2013 a goal that 50% of whatever fluids we use in the wellbore would be these alternate fuels or alternate water that was not fresh water. Today, as a company, we're just over 40%, and in our oldest areas where we first started this out, we're about 56% other water that we're using. And then, as I said, we had to replenish the water, and we had to somehow replace it. We've done projects with other groups, and Nature Conservancy was part of that, on Ducks Unlimited. In each one of the cases, where either another industry or, in one case, a government agency had actually either been very inefficient with what they were doing with water, or it actually destroyed some of the surface water. We went back and we've begun to fix that. Today we've got over 400 million gallons a year of restoration and replenishment of water that we have. And then the final thing is innovation. They talked a lot about innovation yesterday. All the things they talked about yesterday, whether it's moving water, whether it's working with universities on research, we're doing all that. End result, today, on 2/3 of our acreage, in 2015, we were freshwater neutral. We actually gave back to the environment about 200,000 barrels of water. On one area, we're not quite there yet. It was an area we bought at the beginning of 2015, so we've only been able to work on it just basically right at a year. We're about 83% freshwater neutral on that, and it looks like by the end of the year we'll make that goal all the way. So,
well, that's terrific. I think you touched on the three big issues that are in the minds of the public. The utilization of fresh water, especially where there's a scarcity, the possibility of contamination either at the surface or downhole during operations, and then what do you do with water, after it comes back from the subsurface? And that leads to our next two panelists. So, Becky Tomasek, you're in the water treatment, water recycling business. So what's new in your industry, and how do you help Steve and the other operators achieve these goals?
Okay, well, thanks, Mark. Well, obviously in this price environment, $30 oil, $2 natural gas, there's a lot of scrutiny on costs. But in some ways, it's a good thing. I think we talked in the innovation session about it, kind of put it to choke on the industry. It gives us some time to maybe look at our water costs and install some cost savings, some efficiencies. And we at CH2M are really seeing about 5 different trends in this space. I mean, the first one is really low-hanging fruit. It's the installation of instrumentation and controls. How much water is in this pit over here? You can't really improve if you can't measure it, so let's measure it in the first place. And then once you can measure it, maybe install a control valve, install some automation on some pumps so that you can save some operator time. The next big trend is really infrastructure, pipes in the ground. We saw, heard Anadarko talk about that, take some trucks off the road. But along with that trend, what we're seeing is the use of scenario analysis tools, some decision-making tools, so that, you don't want to put a 3-inch pipeline in the ground when, you might, the next upturn, increase your rigs, and that's just not big enough. And along with those scenario analysis tools, it's some water management planning tools so that you can get your drilling team and your completions team and then your water management team that are often different people really talking to each other and saying, hey, this month, if this is our drill schedule, let's plan our water here, plan it beforehand a little bit better. And we've done this with some operators and saved sometimes $20,000 a day in water costs. Another big trend is really water sourcing. We've heard from Anadarko, they're using wastewater effluent. Pioneer just announced a couple of weeks ago they're using effluent from the city of Midland. We have a lot of operators looking at brackish water sources, moving away from fresh water. And then we had one customer come to us, they've got to look at an aquifer, a water source that has high levels of hydrogen sulfide. So they came to us to how do we treat this water so that we can use it for hydraulic fracturing. And they were thinking this would be an R&D project, and it just so happens that we have a reference position. We have already designed a technology, piloted it, and scaled it up, and are operating a plant in Australia with that same type of characteristics in that water. And then the last trend we're seeing is really produced water recycle, and moving from the mobile units to more centralized produced water recycling plants, seeing the economies of scale. This is something we do in the industry. We call it design, build, operate, finance, and maintain. So we would bring in a financial partner, but we would do the rest. And that would serve anywhere from 5 to 10 operators, depending on the location. And it's a really exciting time for us because we already do these things across municipalities, across industries. We already work with governments on regulations and permitting. We work with oil and gas operators. We work with technology players. So it's an opportunity for us, exciting time for us to integrate all of these different areas so that we can help build a water life cycle that's much more efficient when the upturn comes and you need a lot better water system for the industry.
Thank you. I think everyone easily imagines the need for water when you're going to drill new wells, when you're going to do the hydraulic fracturing, and then the contaminated water that's created. But there's another big part of water in the oil and gas industry, and that's produced water. And GE is one of the biggest and most successful engineering and technology companies in the world. What is GE doing in the produced water space?
Great, Mark. Thanks. So produced water is our particular interest in this topic that we're talking about today, and that's where most of our focus and most of our energy is these days. I thought it'd be interesting to maybe offer a little background on produced water. I tried to triangulate, as you look across all the different production methods and different regions of the world, how much water is associated with oil and gas production. And as near as I can figure, it's on the average about 3 barrels of water per barrel of oil. 3 barrels of water per barrel of oil. So there's a tremendous amount of water associated with the production of oil and gas, and therefore it's a big deal. The oil and gas are separated obviously from the water, but then the producer is left with the challenge of managing that produced water. And the produced water, it can be fairly nasty stuff. It's been down in the reservoir, it's been exposed to the oil and gas, it's been exposed to the geology, and therefore, even after the separation, there's going to be some residual organics in the produced water. There's going to be dirt and particulates from the exposure to the reservoir, and dissolved solids, so salt, and sometimes that can be a very high level of dissolved solids in there. So produced water is going to be treated to some extent, no matter what the application is. And the nature of the treatment it depends on the quality of the produced water, and it depends on the management strategy that the producer has in mind. And there's really 3 things that the producers can do if you look at it in a sort of a broad sense. They can recycle, which is a great option. They can dispose of the produced water, or they can clean the water up for a beneficial use, such as surface discharge or agriculture, something like that. So those are really broadly the 3 options there. And again, the treatment strategy depends on the quality of the produced water and what the net effect is. So just a little bit on the kinds of things that can be done and must be done to clean up the produced water. It's a series of operations, almost always, that are done sequentially, and more operations are required to clean the water up to a greater extent, and obviously that adds cost as well. But people typically will talk about primary treatment. This is fairly simple, fairly straightforward, fairly low cost, and it's either mechanical device or simple filtration to take out the free oil, emulsified oil, and all the particulates. So all the stuff that's not dissolved in the water comes out with this primary separation, but anything that's dissolved in the water, any organics and any salt, goes past primary separation. So if more treatment is needed, then that starts to involve maybe a biological treatment, removing scaling and hardness, and then finally a desalination step to take out all that dissolved salt that came up with the produced water. These are the expensive steps. And now this becomes a fairly complex, fairly expensive flow sheet to take the water all the way to desalination. Now, to go back to the North American frac operation for a little bit, what's necessary there and what most of the producers do today is that simple primary separation. And this is suitable if they're going to dispose of the water or if they're going to recycle the water. And it's really terrific that the service companies have figured out how to take this salty water that's cleaned up just a little bit and then adjust the chemistry used in the frac operation so that this can be used. And it was great to hear Steve talk about the extent to which they recycle their produced water. So I think, you know, that's really great. What we're doing in this space now is we've started to create a service business to provide primary separation to the producers. We're not exactly sure where that's going to go in the long term, and clearly there's trends in the industry, but by being in the service business, we'll get that exposure, we'll get to know the industry better and learn what we need to do down the road, and we're already, you know, talking closely with Becky and working with her on some of the things that we're trying to do, see if there's a collaboration with CH2M. One more quick example of produced water, and it's a different example with a very different outcome, and that is with the Canadian oil sands up in Canada. We heard a little bit about that earlier today, but they haven't gotten as much discussion at this meeting as the hydraulic fracturing operations. There, the process, very quickly, if you're not familiar with it, is the oil is, they call it heavy oil or bitumen, and it doesn't flow under normal conditions. So the way they recover the oil is they inject steam into the ground. The steam condenses, that warms the oil up. Now the viscosity reduces, and they pump this water, condensate now, and oil mixture out. They do a separation, and that condensate now becomes the produced water that has to be managed by the oil sands producers. And in Alberta, it's been mandated that that water has to be recycled at greater than, I think it's greater than 90%. So they have to recycle the water. And the way they recycle it is it becomes feed water to a steam generating operation, either a steam generator or a boiler. So it has to be cleaned to a very great extent. So we've worked closely with the oil sand producers over the last number of years to provide a solution that's primary separation, then coupled to our zero liquid discharge solution, which is a thermal evaporator connected to a crystallizer, and that way we get very high recovery of the water. So that's a recycle solution that requires a fairly extensive treatment, but that's the management that's in fact required by the regulations in Alberta. So just a couple of last thoughts here. The technology is available to clean any produced water up to a very high degree, but it costs more to do more treatment. The challenge for someone like us is to make sure that we're developing the solution that's the lowest cost solution that meets the requirements for the management strategy that the producer wants to implement. And the last thing is, I think there's still plenty of opportunities for R&D here. Even in simple primary, there's a lot of challenges there, and we're bringing our R&D teams to work on that, to help figure out how to make that a more robust, lower cost operation. And in the oil sands, we're working with an organization called COSIA, the Canadian Oil Sands Innovation Alliance, to develop a lower cost solution for the water recovery in the oil sands. So I think I'll quit with that.
Thank you, Tom. I want to turn back to unconventionals for a moment, because one of the unique aspects of unconventionals is that a lot of wells are drilled in a given area. And when I was on a committee in 2011 for the Secretary of Energy, looking at environmental impacts of unconventional development, one thing that became apparent is that the cumulative impact of all the drilling in a given area was not really being addressed. And you know, if it's like kind of urban planning, you know, if there was a blueprint that could help minimize the number of roads, the number of pipelines, and a blueprint for water management, water sourcing and water disposal, it might, you know, benefit not only the companies working there, but of course minimize the impact on the people living there. We have 15,000 wells in the DJ Basin. We have 15,000 wells in the Dallas-Fort Worth area, in the Fort Worth Basin. And so, you know, there's big impacts there. Are there examples of sort of companies and government agencies and public interest groups sort of working together to do more regional planning to sort of, you know, come up with these, you know, these plans that would minimize the problems associated with water or other operational impacts?
I'll jump in and try and say something there. I don't know of any deliberate groups that have been brought together that would bring our industry with all the other industries and do a balancing across the whole thing. Part of when we did our freshwater neutral, and I didn't say this before, but part of our objective was to be freshwater neutral by watershed, so that we could at least, if we could do that by watershed, we wouldn't have done any harm to that area that we were in and where we lived and worked. There is kind of I call it an accidental one that I know about. There's actually two of them. In far northeast Pennsylvania, there's been two agencies set up, really various states, and one's 3 states, one's 5 states, that basically take care of the watersheds for the Delaware Basin, and then there's one for the Susquehanna River, and we drill around those. So we are in that, they model that, and in that case, they're trying to do the whole hydrology for the entire watershed, and we're part of that process. But that's all I know about from overall type.
Well, that might serve as a model for other areas to do the same kind of thing, and I think water management at the watershed level makes perfect sense. I want to come back to you, Steve, with another question that the public is very concerned about, and that's contamination due to downhole operations. And the fear that hydraulic fracturing is going to contaminate fresh water supplies is sort of front and center in what the public cares about. And yet, both President Obama and former EPA Administrator Lisa Jackson are on record saying there was no documented case in which hydraulic fracturing was actually the source of contamination. But there is contamination. And when the contamination is investigated, it always kind of comes back to wellbore construction. The well just wasn't built properly, either due to bad planning, but more frequently due to just the operations, something going wrong with the operations and not getting caught at that time. So, what does a company like Southwestern do to make sure that the people in the field are doing things right, especially when you're highly dependent on contractors and there's incentives to kind of go fast, but it could leave behind a really terrible legacy if things aren't done right from the beginning. So how do you, what do you do as a company to make sure that doesn't happen?
Yesterday there was a little bit of discussion in the innovation part of it, where they talked about making sure that your employees were educated, making sure that all the people that work with you and the vendors and the services know what the issues are and how to work in those areas, and you do that. But the basic thing that we've done as an industry is I'll call it a redundant approach. Whatever we do, we try to do a redundancy. So if it's something downhole and you're producing something, or you're putting fluids downhole to do the completion, you're going to have 2 strings of pipe between whatever you're doing and whatever that formation is to make sure that's the case. If you're completing the well, those shallow groundwater have 2 strings of pipe between them, and there's cement that's there. And then whether you're on the surface, you've got the right not only to worry about the groundwater, but the public has the right not to have that whatever's in the surface go where it's not supposed to, and you do redundancy there, and then you monitor. And this goes back to comments of before, and comments I made yesterday is whether it's monitoring with people, whether it's monitoring with a room someplace that monitors all the wells in the company, however that is, you've got to monitor, and part of that monitor is done through a regulatory process, part of it you do yourself. And in our case, what we do, just like they talked about yesterday, we've got everything instrumented up. We're monitoring 24 hours a day on all of our tanks, all of our facilities that go that direction. And we do that both on the water and methane side, so we've got both those covered.
So systematic monitoring and centralized control and command systems are becoming more frequent and taking a lot of these issues off the table in a more sort of high-tech. You know when something goes wrong when it happens instead of waiting for it to be reported. So that's.
And I'll just give you an example. Yeah. You don't normally think about this, but when you're have a large rainstorm come through, one of those redundancies you have at the surface is you have these berms that whatever tanks, whatever you have before you, this berm's 3 times bigger that can contain in case there's a leak in the tank. Well, if it rains hard enough, you fill that whole berm up with water, and if there was anything in there, it goes over the top. Well, part of this automatic monitoring you do is that you set a monitor well down that berm. If it starts coming up, you get people on the field long before then. You can take care of it before you get to the problem. So it's not just responding because there is a problem, but it's predictive with what you're doing, and that a lot of that is digital now, where it was people before.
Okay. Well, to use these centralized treatment centers and command and control, you not only need the information, but you need access to the water, and that suggests pipelines and other things. We heard about that yesterday, and the success of using that to take vehicles off the road. And when the public is surveyed, usually traffic and noise are at the near the top of their concerns. So are there mechanisms while you're drilling and completing and needing lots of water that you can temporary pipelines or whatever, so you can get those trucks off the road, and similarly to get the flowback water, to a centralized place where it'll be recycled or treated or whatever. How does that work now? Are we still relying on trucks, or are alternatives being widely used?
We're seeing more and more adoption of pipelines. In some cases, it is flexible. You still see the lay flat hose out there to add some flexibility, but we're seeing more of permanently installed pipes that go from a central storage location to a central processing facility, and then the treated water would go back via pipeline from that central processing facility back to a different storage in an area. And then a more temporary type of pipe is used to take it to the next drill site. Oh.
And of course, there's big economic drivers about whether disposal or recycling is less expensive, and the water transport is a big part of that equation. And as you said, Steve, every place has its unique issues, and I guess you answer that economic question on a case-by-case basis.
Yeah, there's two pieces to it. There's, and I mentioned earlier, if you don't do anything through pipelines, I talked about that yesterday, if you don't do anything through pipelines, just hauling things, not just water, but just hauling things, water is about 3/4 of this. It's between 10 and 12,000 truckloads, large semi-truckloads of materials that you use on a well site. You're literally building a factory every time you're on that well site. And if you can cut out that water part of it, you cut 75% of the traffic out. Now, it's a little bit different story, and we have, for instance, in Arkansas, we do everything with temporary pipeline at the surface for the fresh water. When you start talking about treated water that hasn't been treated all the way back to fresh, and you start putting that through pipelines, either underground or on the surface, then you have to start thinking about other liabilities or other issues to make sure that there's not leaks in those pipelines or those other things. And so I think what you'll see a lot of times, it goes back to economics, but it also goes back to what the ultimate safest way to move water. And in some cases, it's unfortunate, but in some cases, actually moving it through a truck, especially if it's not completely treated all the way back to fresh, is the way to go. And to put this in perspective, if I'm moving water in a truck, $10, $12 a barrel. If I'm putting it through the pipeline, $1.50, $2 a barrel. So I'd much rather put it in the pipeline.
Tom, here's a question for you. I know GE is working on technologies to capture and utilize stray gas all along the value chain. It's a great idea because you capture it as economic value, you capture it and it's not emitted to the atmosphere. And there's a question about flare gas and whether it could be used as an energy source to help purify water. But more generally, are there, produced gas, which, when there's not a pipeline available, or even if there is a pipeline available, you have energy at the drill site, which, are there technologies that are sort of locally sourced with energy and then locally applied to a problem of contamination?
I think all those are options going forward. With respect to the specific question, those are activities that are taking place in our oil and gas business, and I haven't seen an update on that in some time, but I know it's an initiative that we want to work closely with the producers in. I think this issue of making sure that we minimize escape methane is a really good idea. Some of the technologies that would be required with respect to water if a producer wants to go all the way to fresh water, one of the things we talked about a little bit at breakfast is that last step, that desalination step, actually requires quite a bit of energy. You know, you can't fool Mother Nature. You have to supply the energy required to mix sodium chloride or other salts in the water. You can make that process more efficient, but there's always going to be an energy barrier there. And then you can access that energy locally, and some types of technology may be more amenable to use you know, flared gas or the energy that could come from flared gas at a particular site.
In the panel with, on innovation, upstream innovation yesterday, Doug Suttles made, I think, a very important point about regulatory systems. And I first stumbled in this serving on a committee looking at the Deepwater Horizon accident and what reforms are needed to the regulatory system to minimize the chance of something like that happening again. And you know, it's easy for regulatory systems to be prescriptive. Do this, this, and this, and you'll make us happy. But really, you really want regulatory systems to be goal-based. And one of the things you know, we've talked about is having, you know, a well completion, a well design that creates redundant barriers to contamination, so that if one barrier fails, you still have a backup. And that's not in all the regulatory systems, but I know companies like Southwestern have that as one of your basic principles when you design a well. So can you know, address that issue and how you approach it?
You know, there's certainly, and I talked about it yesterday, and there were some questions about, well, there were certain accidents or things out there. The public and our employees deserve for us to have zero incidents. That's not going to happen, but we need to figure out to do everything we can to get there. And part of that, there's some uniqueness to what we do. And just a simple example of that is part of this redundancy early on in Arkansas, the commission came up and said, what we want you to do is cement all the way back to the surface between these pipe, because it just made sense that if you cement it all the way back, then that would give more isolation. The issue is that if you did that and you ever had any kind of problem below where this was at, you had no way of fixing the problem. And yet if you did a combination there, you could actually build more redundancy in the system. And so what you had to do there was go back to the regulator and said, well, that may be the case in some places, but it's not the right thing there, and show them why. Build a database, and then after we build a database, we were able to change that rule so we could keep that redundancy going. So I think it's an ongoing process. And going back to your goal ought to be that we have no problems, but you can't do it prescriptively. And so you just have to work with them in each one of those areas, and each one's going to be a little bit different in how you do it. And so you've got the top level, and that top level may be federal, maybe the state, or maybe the local, and then you just work with them as you go through it.
Yeah, it's easy for regulatory bodies to be prescriptive. It's easy to check, you know, that all the boxes are satisfied, but it's not effective. And they have to be engaged in what's going on, and one way to do that is to present a plan that achieves their goal, and to get there together. We have one question about hydraulic fracturing, and I guess it's for you again, Steve. What advances are there that both minimize the amount of water, lower its costs, make it more efficient? And it wasn't asked here, but it often comes up. What are the alternatives to using water for hydraulic fracturing, and minimizing some of these problems by just using nitrogen or CO2, as has been used for hydraulic fracturing at other times in other areas?
Let me kind of explain very quickly why you want water or why you want some kind of fluid. The fluid does two things. The first thing is it's what actually causes the cracks in the rock. And so when we start talking about some other medium that's not a fluid, it's very difficult to get the right characteristics downhole to actually make that crack in the rock. So you can do liquefied natural gas, you can do various CO2. Now in the case of CO2, it's actually liquid that you're putting, it's cold and you put it downhole liquefied. But it actually breaks the rock, It's the one that propagates the frac out into the overall formation. And then what you do is you send a proppant down behind, and it has to carry that proppant also. It ends up that depending on where you're at, again, the region, how deep you're at, what kind of frac it is, there's all different kinds of fancy fluids you could use, but the base for that is almost always water. Now, there are a lot of experimentation, and we as a company have had some of the service companies do some very high-tech experiments on some of our wells where we actually allowed them to go in and do something on a fracture stimulation well where they're trying to use a very, very small volume of fluid and maybe not be exactly water-based, or in some cases allow more fluid to come back and have it cleaner when it came back. But you have to have something that actually breaks the rock, and so it's going to be some kind of fluid that goes down there. I think there's kind of holy grails out there. That's one of those holy grails that we're working on as an industry, and I would say before we'd see much new technology where it's not water-based, you're probably 5 to 8 years out, 10 years out.
Yeah, I could reinforce that point. 'Cause we're doing research on that at GE and looking at a number of options down the road. But I support Steve's point. It needs to be incompressible for it to work, to break the formation apart. And water's a pretty good answer, so I agree. I think we'll be with water and dealing with water issues for the foreseeable future.
So the switch from fresh water to brackish water is a logical thing to do. And yet the brackish water presents its own challenges, so I guess that's created a whole new business opportunity for companies like CH2M, that you have to treat the brackish water to make it good enough to use in drilling and fracking. And what kinds of things are you doing in that space?
Yeah, in that space, it depends on where you are, what the aquifer is coming from, and it can be as extreme as the brackish hydrogen sulfide water. But just, general brackish source, you'll treat it with some primary technology, as Tom talked about, maybe do some filtration and get any of the suspended solids that are out there. But as the industry has evolved over the last 5 years or so in this shale space, the operators and the service companies have done a really good job of manipulating their chemicals to deal with that brackish water. So it's opened up a great water source that's non-fresh water. Yeah, if you do need to treat it, but then also and add to the chemicals so that it can be used for hydraulic fracturing.
As someone who lives in a state that's, we think, emerging from a 4-year drought, and there being tremendous controversy about how much water is being used for almonds and avocados, is produced water a potential resource? Is there anything on the horizon, Tom, that you might allow some of that water to be of beneficial use?
Well, a couple of things. First of all, on the grand scale of things, the amount of water used in these operations is really tiny. And you compare that to what's used in agriculture, and it's orders of magnitude less. Regionally, the amount of water used in these operations may create an issue, but if you look at it on the grand scale of things, the amount of water used in these operations is pretty small. So I don't think it's an answer for the agricultural problem. And then just the other dimension to that, as I started to allude to a little bit earlier, the cost to take produced water all the way back to fresh is fairly expensive today. Now, we're working on that, and we hope there'll be advancements there, especially to take capital costs out, but that the energy cost associated with separating the salt from the water is always going to be there.
We only have a couple minutes left. I want to give each panelist kind of a chance to sum up and say what's most important in this space to them and their companies at this time. Tom, Steve, shall we start with you and go down the line?
Yesterday there was a discussion about what can the industry do, and there's a lot of talk about it. We need to educate, we need to tell our stories. We need to do all that, but I think the other thing the industry needs to do is at least try some of these things where we really recognize the issues. Our customers, it's not in my mind, it's not a social license. We have customers out there. It's the people that live in the community. A lot of them are our employees that live in the community. And so we talked yesterday about innovation, about taking a leap out, take a leap of faith, try to do something that's a little bit different, try to solve the real problem. And I think in the water arena, if we try to do that, we can be very successful. I'm already starting to see some things. I'm hearing what they're doing. And so I think that's the message I want to send is we're going to take those steps as an industry that are going to, may at times not work, but we'll see what we can do.
Becky?
Well, hydraulic fracturing's been around for decades, horizontal drilling's been around for decades, but the combination of the two is really pretty recent. And this boom that we've had, it was fantastic, but the water life cycle is on that flat part of the S-curve. It's still the whole water sourcing, transport, recycle, disposal is still in the early days. So I think it's just an exciting time to optimize that whole life cycle and bring new technologies and get into the steeper part of the S-curve and with new technologies in the water space. And I think it's going to take some of these partnerships that you talked about, Mark, and regional partnerships between different stakeholders.
Tom?
I guess I would just say one way to think about water in this space is it's really an enabler for oil and gas production. And if you think about where we are in terms of the proven reserves and where new reserves will come from, it'll be unconventional sources, and their water is an inherent part of the production process. Hydraulic fracturing and the oil sands operations being two very good examples of those. So water plays a very important role there. We want to play our role as a technology provider to work with the producers to make sure that we do that effectively and safely.
Thank you. You know, if there's a silver lining to this down cycle, it provides an opportunity to kind of consolidate what we know. And so as we come out of the down cycle, we're doing a better job both in the production and in the environmental parts of things, and water is a big part of that. And I think we can look forward to every aspect of this development being done better in the future than it's been done in the past by taking advantage of everything that has been learned. So please join me in thanking the panel for a great session.